Hello and welcome back to my Physics Online Video Lecture Supplement series. In today's video, I'm going to continue my lecture set number 9 on statics and equilibrium and look at a few problem solving and applications portions of statics and equilibrium. And recall from part 1 of this set of lectures that if you have an object which is in mechanical equilibrium, then the object is going to satisfy two conditions and therefore two equations. The first is translational equilibrium, by which we know that the sum of forces acting upon that object should be zero. And that, of course, is Newton's first law as well. The second condition is rotational equilibrium, under which the sum of all torques acting on an object must also be zero. And so we kind of discussed that a little bit in part 1 of this lecture series. The point here, though, is that not all equilibria are equally stable. And moreover, I'm going to talk a bit about a few simple machines today which make use of these two equilibrium conditions. And as a sort of opening picture, here is this giant rock in the Garden of the Gods in Colorado Springs, Colorado, which is actually satisfies both of these conditions of equilibrium. It is in fact balanced on this little outcropping on this other rock. You can see that it's not falling in any particular direction. The total force on this rock is zero. The total torque on this rock is zero. So the first thing I wanted to talk about is stability. So there's basically three types of equilibrium. You can have a stable equilibrium, an unstable equilibrium, or a neutral equilibrium. Stable equilibrium basically means that if you displace the object slightly from its equilibrium position, then there will be a net torque in the opposite direction from the displacement, such that the object moves back to its original position. An unstable equilibrium means that if it's displaced slightly from the equilibrium condition, then the net torque is going to move away from the direction of equilibrium. In other words, the net torque will be in the same direction as the displacement, and the object will fall out of its equilibrium entirely. Neutral equilibrium basically means if you displace the object from its equilibrium position, then it doesn't really experience a net torque towards or away from the original position. The equilibrium is basically independent of displacement from the original position. So let's look at a diagram that sort of contrasts between stable and unstable equilibrium. So if you have a stable equilibrium position, then you're acting more or less like this pendulum. So the pendulum here is in equilibrium. It's at the bottom of the string which is supporting it. The string is basically vertical. And if you were to displace this pendulum, as in this right half of this image, then there would be a net force and a net torque that would rotate this pendulum so that it goes back to this vertical position. And so basically when you pull the pendulum away from its equilibrium position, it will attempt to swing back to its equilibrium position. Now it may overrun that equilibrium position, but the point is that it will be swinging back towards it initially. And another way of looking at this is that your stable position is usually the local minimum for potential energy. So the pendulum is at its lowest potential energy when it is hanging straight down. Granted, this may not be zero potential energy. It may be above the ground somewhat, but so long as the pendulum remains intact, this is the lowest potential energy of this pendulum. If you were to remove it from this position by pulling it aside, you are actually raising its height and therefore giving it some additional potential energy. The bottom half of this diagram illustrates what unstable equilibrium might look like. So this pencil when it is like this, balanced on its tip, is in fact in equilibrium. It can stand on its tip straight up. But if you were to bump the pencil at all so that it tilts slightly, then the result is that the contact with the ground might apply an upward force, the weight might apply a downward force, and those two forces are going to create a pair of torques, which will cause the pencil to rotate so that it falls to the ground. Notice that this right here, this position, is actually at a potential energy local maximum. So this is the highest potential energy that you can give to this pencil. The center of mass is the highest above the ground that you can give it. If it's lying on its side, it's at the lowest point on the ground. So the pencil on its side actually satisfies what would be called a stable equilibrium. And this pendulum, if it was a solid pendulum, if it was flipped so that it was straight up, would actually be satisfying an unstable equilibrium. The other type is neutral equilibrium, and there's another sense in which that pencil would be in neutral equilibrium if it is lying on its side. So it's a stable equilibrium in the sense that the pencil is not going to spontaneously rotate so that it stands up on its tip. It is also a neutral equilibrium in the sense that if you look at the pencil from a different direction, you will see that if I were to roll the pencil a little bit, it may come to a stop at some new position, some new angular position. So a perfectly smooth marble on a perfectly flat and smooth floor is in pretty nearly a neutral equilibrium position. And the rotational and translational positions of that marble will be irrelevant regarding equilibrium. If it is displaced, it probably isn't going to be moving towards or away from its original position so long as you don't displace it by, say, flicking it to set it initially in motion. So that pencil that I used as an example on the previous slide is actually therefore a case of limited equilibrium, or limited neutral equilibrium if you would like. Basically, it is in a stable equilibrium as regards whether it's going to flip to stand on its tip, but it's in neutral equilibrium as regards to whether it rolls or not. So basically that's stable equilibrium along its length and neutral equilibrium in the rolling direction, the lateral direction, if you will. One thing which determines the stability of the system, a big thing actually, is the system's base of support. So there's two possibilities with regard to the base of support, broadly speaking. The first is that the center of gravity is below the base of support. The other is that the center of gravity is above the base of support. So in this diagram, the center of gravity is actually above the base of support. And if the center of gravity is actually below the base of support and the object is in equilibrium, then it will be in stable equilibrium. So rolling back a couple slides, the center of gravity of this pendulum is probably located somewhere in the ball, and in fact, if it's a uniform ball and a massless string, then it will be in the very center of the ball. Since the string probably has some mass, that maybe means that the center of gravity moves up slightly, but in any case, the base of support for this is actually where this string is suspended from whatever it's hanging from, the ceiling or a lever arm or what have you. So this is going to be stable equilibrium because the center of gravity is actually below the base of support. The pencil, the center of gravity is right here where this arrow representing the force of gravity is acting from, and it is above the pencil's base of support. Similarly, with this refrigerator, the center of gravity is above the base of support. And so we have to do more to figure out whether the equilibrium is going to be stable or not. It could be stable, it could be unstable. The pencil on its side, for example, is also center of gravity is above its base of support. A box lying on the floor, or this refrigerator-freezer combination, has a center of gravity above the base of support. So typically, when your center of gravity is above the base of support, the result is that a small perturbation tends to be stable and a large one tends to be unstable. So here is the refrigerator-freezer under stability. Here is a small perturbation. It's tipped slightly to the side, but it's going to, if you were to stop pushing on it to tip it, it would actually tip back this way so that it remains upright. If you tip it too far, however, it's going to fall over on its side. And the basic rule of thumb is if the center of gravity is above the base of support, then the equilibrium will be stable. And if the center of gravity is not above the base of support, then it will not be stable. And by above base of support, what I mean is, here is our base of support, here is our center of gravity, this one is stable. Here's our base of support, here is our center of gravity. This is, if you drew a vertical line, would go through this section of the freezer, therefore the freezer is going to tilt so that this is the section that is back on the ground. Over here you have a non-stable condition. It's going to actually fall over on its side. That's because if you were to draw a vertical line from the center of gravity downward, you'd find that it does not pass through the original base of support, and therefore it's going to tip over. So a second rule of thumb is that the wider the base of support is and the lower the center of gravity is, the more stable the object will be. So you can see that the freezer refrigerator, if it was lying on this side, would have a much more stable equilibrium than when it's on this side. You have to tilt it a lot farther away from this side before it will not return to lying on this side than you do with this side. This ties into a thing called balance. And our stability, which is balance, depends largely on the stance that we take. If you stand with your feet very close together, you're going to tend to be less stable than if you crouch slightly with your feet a little wider apart. Oddly enough, if you look at other animals, like say a chicken, then this may be a little bit different. The chicken, for example, has a center of gravity that's actually lower than the base of support, if you count the base of support to be its two thigh bones. So the chicken in many ways acts like a pendulum, with the center of gravity being below its hip, and it tends to be very stable both front to back and side to side. So front to back, the stability has to do with where is the center of gravity with respect to these two hip joints. The chicken actually kind of swings like a pendulum, or can swing like a pendulum as far as that is concerned. So it's very stable equilibrium. Side to side, it acts almost more like that refrigerator in that you can tip it enough and it will fall over sideways. Chickens tend not to fall on their face, however, as a result of this center of gravity being relatively low compared to where its base of support in that direction is. So I wanted to go through a little bit of an outline of problem solving for equilibrium problems. And basically, what is the approach for solving these kinds of problems? So first, you should determine the known and unknown quantities in your system. Second, you can determine the extent to which the system is in equilibrium. Is it in translational equilibrium, in which case the sum of forces is zero? Is it in rotational equilibrium, in which case the sum of torques is zero? Or is it in both, that is static equilibrium, in which case both forces and torques must add to zero? Third, once you've done that, you should draw a diagram of the system. And in fact, this third step may be sometimes your first step, because it lets you label what all the forces are and then determine which ones are known and unknown. So this order is a little bit your call, which order you go in. So for example, if you want to find the center of gravity for a person, you might do it by basically putting a scale under the person's feet, having a board run from that scale to a second support structure, and then the person can lie down on the board. The scale will read how much force the scale is applying to keep the whole system in equilibrium. You would also have needed to weigh the board alone and maybe the person alone on the scale. So from there, you basically have the force from the scale. You know what the weight of the person is. You know what the weight of the board is. What you don't know is where this weight of the person acts at. It's going to act at his center of gravity, but you don't know where that is actually located. You know where the board's weight is acting. It's going to be the center of mass for the board. You know where the scale and the fulcrum are both acting, but you don't necessarily know what force the fulcrum is applying. You may or may not, in fact, have weighed the board that the person is lying on, so you may or may not know the actual weight of the board either. So once you've set up the problem in this way, you now can either use sum of forces equals 0 or sum of torques equals 0, or usually both. And last but not least, you solve your equations and then you can double check your work by, for example, once you solve for what the normal force from this is and where the center of gravity of the person is, you might change your axis of rotation to somewhere else and see if you still get 0 torque on the system. All right, let's look at an example in which we try to find where the position of the center of gravity for the person is based on having some information about the person's height and weight, and then a scale reading and the weight of the board upon which the person is lying. There are two basic equations for which we are going to be solving here, of course. One is that sum of torques is equal to 0. The other is that the sum of forces is equal to 0. Recall that the torque is given by the radial distance times the force times the sine of the angle between the force in question and the radial distance in question. Now, in this case, the radial distance is always horizontal, the force is always vertical. That means that this sine of theta term is always going to be equal to 1. Now, the other thing is that we should look and see whether the torque will be clockwise or counterclockwise on this figure. And to do that, we need to choose an axis of rotation. We're going to go ahead and choose that axis of rotation to be right here at point O, where his head is and where the fulcrum is located. So this first torque right here, let's do the sum of torques, and we're going to make it positive if it's counterclockwise and negative if it is clockwise. So the sum of torques, this one right here is normal force times this distance, which is 0. So the first one actually is just normal force times 0, so we don't have to include that force in our calculation. Next force is from weight. The weight is tending to make things spin this way. This weight also is tending to make things spin this way. This force is tending to make things spin this way. So we would have minus the weight of the guy times the distance from this axis of rotation to this center of gravity. So I'm going to call that RCG. And then again, minus weight of board times the half the length of the board, since the center of gravity for the board is located halfway along the board's length. And then that's going to be plus the force from the scale times the distance, which is the length of the board. So if we were to combine this condition and this condition, what you basically end up with is that the weight times the center of gravity distance is equal to the force from the scale times the length minus the weight of the board times the length over 2. So that is our torques equation. And let's see if we have numbers that we can plug in for each of these things. Well, looking up here, we're given that the height is 180 centimeters, so this is the length. This right here is the weight of the board. This right here is the actual weight of the guy, and this right here is F. So actually, we can solve for the equation with just this information that's been given without having to do anything further. So this right here is basically saying that the center of gravity distance is the force times the length over the weight minus the weight of the board over the weight of the guy. Kind of put those two backwards. Weight of the board over the weight of the guy times the length over 2. So that is going to mean that the center of gravity distance is the 370 newtons over 750 newtons times 180 centimeters minus 50 newtons over 750 newtons times 180 centimeters over 2. So now we can plug all those guys into our calculator, and what we'll get is that the center of gravity position is located about 82.8 centimeters from this guy's head. So this distance right here, from here to here, is 82.8 centimeters. So notice that we ended up only using up one equation from all of that. The reason why is because we were given more information than you usually have to work with when doing this in the lab. Now granted, it's relatively easy to find what the force of this board is. For that matter, you could replace this fulcrum with another scale and get a scale reading here and a scale reading there. You would find that the two scale readings are different, and in fact we could at this point try to solve for what the scale reading would need to be here. For that, you would use this other equation, the sum of forces is equal to 0 equation, to get that the normal force there is equal to the sum of the two weights minus the force from the other scale, which would be 750 plus 50, which is 800, minus 370, which leaves us with 430 newtons. So if you happen to have a scale here, you'd get 430 newtons. I wanted now to discuss the concept of mechanical advantage and how it applies to a variety of simple machines. So a simple machine is basically a device which you can use to increase the amount of force which is applied to an object. So basically it's a force amplifier, if you will. It takes the amount of force that you put into the system and enhances it by applying more force to whatever object, whatever load you're trying to move, than the force that you're necessarily having to put in. You may think of it as a way of decreasing the amount of force that you have to put into a system to accomplish a given task. Now, the thing is that these machines are going to conserve energy, so they can't do more work than whatever amount of work you put into the system. What they do, however, is make a given job easier by reducing the amount of force that you have to put into the system in order to do a given task. Now, the ratio of input to output force is what's called mechanical advantage. So if you apply a force to the end of this hammer or to this lever, then the lever or hammer is going to apply some amount of force to the load or nail. And that force that you put in is going to be less than the force that is applied to the load or to the nail. And that ratio of force that you pushed with versus force that was applied to this object you're trying to move, that's the mechanical advantage. So the first of our simple machines is the lever. And what a lever does is it uses a balance of torques to apply more force to an object than the force that's being applied by the user. So here is a guy that's using a lever to basically move a boulder. And you can see that there is a one radial distance between his pivot fulcrum and where he's applying a force, and a smaller radial distance between that same pivot fulcrum and the object that the lever is applying a force to. So that means that the torque on this system is balanced so long as this is not accelerating. So that means that the torque that he applies in the clockwise direction here is balanced by the counterclockwise torque that is being applied to the system by this boulder, which of course is found by force of boulder on rod is equal to force of rod on boulder. That's Newton's third law. So that means that if you move the fulcrum closer and closer to the boulder, you get a larger and larger mechanical advantage. So the mechanical advantage of a lever is actually going to be given by the radial distance between you and the fulcrum divided by the radial distance between the fulcrum and the thing that you're applying force to. This is why it has been said before, give me a long enough lever and a good fulcrum and I can move the world. One application of the lever, a common everyday tool that uses it, is the nail puller of a hammer or of a crowbar. And basically the pivot point is usually really close to the nail's head. So there's usually like a little flat part on the bottom of the crowbar before it gets to the prongs that you fit under the nail. That flat part ends up being the pivot point. And so if you apply a force to the far end, you have a very large radial distance between your hand applying that force and that pivot point as compared with the distance between the pivot point and the nail. Now again, the part that matters, the distance that matters, because this is torques, is the perpendicular distance from pivot point to your force being applied by the hand. So if you're pushing down, it's the horizontal distance that matters, not the total length of the bar itself, although as you can see the length of the bar and the horizontal distance can be related because the length of the bar itself is effectively the hypotenuse of a right triangle, in which the actual length that matters, the perpendicular length or the horizontal length, is effectively the base of that same right triangle. In any case, a very small amount of force applied here generates a relatively large torque that must be made up by applying a very large force to the nail in order to balance torques on the system. And so that's why it's so much easier to pull nails with a long-handled crowbar than it is with a hammer, and why it's so much easier to pull with a hammer than, for example, with your bare hands. The next item that I wanted to talk about, the next simple machine, is a pulley. And a pulley, when working alone, only really is going to change the direction in which a force is applied. That means that as long as there's no friction in the pulley, it's going to have a mechanical advantage of just one. However, we can use a pulley to change the direction in which we have to pull in order to move an object. So this sometimes gives us a physiological advantage instead of an actual mechanical advantage, because it may be easier to pull, for example, straight down or down at an angle in order to lift an object than to grip the object from below and lift it upwards. Also, we can do some tricks like attaching a weight to the other end of the rope, which then would help us. If this is 100 pounds and I tie a 50-pound rock to this other end of the rope, then I only have to pull down with 50 pounds in order to lift this 100-pound block. With that said, you can combine pulleys, and that is going to allow you to increase the mechanical advantage. Case in point, you can use something like this block and tackle setup. You increase the mechanical advantage to some extent, up to a factor of 2 for each pulley added, although it's not always going to be a factor of 2. For example, in this system right here, if you wanted to pull up this 100-pound weight, if you ran a rope from, say, an overhead support, ran it under a pulley that's attached to the weight, and then ran it over a second pulley attached to the overhead system, and then you pulled on the end of the pulley, you'd only need to pull with 50 pounds in order to lift this 100-pound weight. However, and that's assuming, by the way, no friction in the pulley, no weight in the rope, etc. However, you still have to have 100 total pounds applied to the weight to lift it. Where those come from is that you get a tension force of 50 pounds here and a tension force of 50 pounds here. And as long as these are being applied basically vertically on this pulley, that's what you'll get. So you're going to get 50 pounds, you're going to get 50 pounds. And as long as the vertical component of that weight in each of these ropes is 50 pounds as acting on the pulley, you will in fact be able to lift this 100-pound weight. Now, if you're off at some angle so that 50 pounds is the total tension in the rope, as in this diagram, you may or may not actually lift this 100 pounds. You may have to apply a little more force just to get the vertical components to be 50 pounds. So it's going to depend also on what angle this rope is at and this rope is at. Now, with that said, the other thing is that you have to make up some additional force in order to get this thing up off the ground, and that comes out of this support structure. So here again is another setup that's similar. This is a more proper block and tackle in which they've basically run a rope. It goes around one pulley, goes around the other, goes around the second side of the pulley, goes up, comes over a pulley. If you're able to get 25 pounds of vertical tension in each part of this rope, then you can lift this 100-pound block. But notice, you have 25 pounds now pulling here and 25 pounds pulling here on this pulley. That's 50 pounds here. You have another 25 pounds pulling on the structure here. So that's, if this was vertical, that would be 75 pounds. And you have an additional 25 and 25, which is in total actually 125 pounds total that this upper support is having to support, whereas you're applying only 25 pounds, and that's what ends up lifting the block. The other trade-off in this is, how do we make sure that energy is being conserved? And the answer is that for each additional rope or each additional pulley, whichever you want to look at it as, you end up having to pull this rope twice as far in order to move the object in the same distance. So your force times distance, whereas your force is halved, your distance is doubled, and so the amount of work done is the same. And of course, if there's friction in this system, then that's going to reduce both the mechanical advantage and increase the amount of work that you have to do in order to lift the block. Our next object is a wheel and axle, which is drawn here. This is basically the wheel and axle for lowering a bucket into a well. Sometimes it's called a crank and wheel. Basically, you have an input force that's being applied to either this wheel or to a crank. A crank would basically just be a single spoke sticking out that you can apply this force to. What you do is it turns the wheel and it turns the axle shaft together. And you apply a large torque here with a small force because you have a very large radial distance, and that's going to apply the same torque over here but it's going to basically be over a smaller radial distance. So that's sort of twice the force can be applied if this thing is half as wide as this one is. So your mechanical advantage basically is going to be whatever the radius of the wheel is divided by whatever the radius of the axle is. And notice that if you take the inverse of that distance, the radius of the axle divided by the radius of the wheel, you get how far the bucket is going to move versus how far you have to move. So once again, an equal amount of work is put in by you as is done against the bucket. So let's look at another example, and this one is with a wheelbarrow. So what we're ultimately going to try to figure out is what's the mechanical advantage of the wheelbarrow, how much force do you need to lift it, and what's the normal force from the ground going to be. All right, the mechanical average part is going to be given by this perpendicular length versus this perpendicular length. You could think of this as acting either as a lever or as a wheel and axle, depending upon how you want to imagine it. Either way, you're going to get the same mechanical average. That's going to be basically RI perpendicular over RO perpendicular. And given the numbers in this problem, what that looks like is that we have 1.20 meters, so 1.20 meters here, divided by 16.0 centimeters should be our basic mechanical average. Now, with that said, the length that we've been given is the length of this arm. So this is 1.20 meters. And we're told that it's at a 15-degree angle. So if we wanted to find this length right here, is basically going to be given by that length times the cosine of this angle. So we need to include a cosine of 15 degrees here in order to get the full mechanical advantage. And in fact, you could basically notice that as you rotate this, the center of gravity is going to rotate along with this handle. So as long as you basically keep some consistency, cosine theta can go on top and bottom. As long as you're consistent with that, you've got a perpendicular distance here. As this thing rotates, this dot will rotate like so. That's going to decrease the perpendicular distance, hence this cosine of theta part can cancel out. What you get is basically 1.2 divided by 0.16, since this is in centimeters, which is a total mechanical advantage of about 7.5. All right, so that's A. B, we want to know how much force is needed to lift it. And the load was given as 66.5 kilograms. Well, the force needed to lift it, should be weight of the wheelbarrow divided by the mechanical advantage. So that's going to be 66.5 kilograms times 9.80 meters per second squared divided by the mechanical average, which we just found, of 7.5. So that's going to give us approximately 86.9 newtons. So 86.9 newtons to lift it versus an actual weight of 652 newtons. So again, that's a ratio of 7.5 to 1 between the actual weight and the force needed to lift it, hence the mechanical advantage. The normal force from the ground can be found using our free body diagram and Newton's first law. Basically, what we have is that the normal force plus the force that's being applied to the handle minus the weight of the wheelbarrow should be equal to 0. And so the normal force should be whatever is the weight minus whatever is the applied force. So this applied force is what we found in the previous part. The weight, of course, is that 652 Newton number that I mentioned, 66.5 times 9.80. So the normal force basically ends up being 651.7 minus 86.9 newtons. And so that gives us a total of 564.8 newtons, or if we round it off to three significant figures, 565 newtons. So that is the normal force magnitude. And if you want the direction, it's obviously up. So I wanted to talk a little bit about torques and equilibrium in the body, just because I know that we have quite a few bio majors in the course. So the concepts so far discussed they really do play an important role in biology, in as much as that our posture tends to place our center of gravity above our hips and above our base of support. And so there's a variety of things that can be said about that. One is that if we're carrying a load of some sort, then we tend to shift our posture slightly in order to basically keep our center of gravity above our base of support. So the guy carrying the heavy briefcase has to lean slightly so that his center of gravity stays above where his 2 feet are located. Basically, the base of support is his 2 feet here. This girl who's carrying the heavy backpack tends to lean forward a little bit and tends to try to keep sort of 1 foot ahead of the other so that she can lean a little bit and have her base of support, which is between this foot and this foot, still underneath the total center of gravity of the whole person. And if we are using good posture, then we tend to be supported by our hips. And if we use a bad posture, then we end up having to apply additional torque to ourselves from our back. And that actually can put some extra strain on our back muscles. And that's how people end up having bad backs later in life. So what I want to do at this point is look at a few different examples of equilibrium, some with bio applications, some not. So some of these are specifically for those of you who are pre-meds, and then I have also another one that is not specific to pre-med for everybody else. So let's look at the equilibrium of a weighted arm. The basic question of this might be, suppose you decide to lift a mass in your hand, like your physics textbook, and you hold it there so that your elbow makes a 90-degree angle. In other words, your arm is parallel to the ground. And the question is, how much force do you have to apply from your bicep muscles and your tricep muscles in order to hold this mass up in the air? Now note, the total weight of this mass at 4 kilograms, the weight is a little under 40 newtons. So the question is, how much force do you have to apply through your muscles in order to do this? All right, first step at this point, because we've already sort of drawn our diagrams here, have them drawn for us, is we need to identify what are the known and unknown quantities. So we can see that this weight and this weight are both given. This distance and this distance and this distance are both given. The only unknown quantities that we have to contend with are these 2 forces. So I'm going to go ahead and pick this point right here to be my axis of rotation. So our sum of forces equation basically says that the force from the tricep muscles, which is labeled Fe in this diagram, plus the force of the bicep muscles, plus the weight of the arm, plus the weight of the book should be equal to 0. And looking at which direction each of these forces act in, we can basically say that the force on the elbow and the weight of the arm and the weight of the book should be equal to the force on the bicep. So force on the bicep is equal to force on elbow plus force from the weight of the arm plus the force from the weight of the book. So that is our first condition. Second condition is sum of torques is equal to 0. Now, again, I've picked this to be my axis of rotation. So let's see whether it's a clockwise or counterclockwise torque in each case. This one right here is applying no torque because it's acting right at the axis of rotation. This is applying a counterclockwise torque. So that one is positive. Basically, radius 1 times force of bicep. This one is clockwise, this one is clockwise, so we're going to have some minuses here. R2, weight of arm, minus R3, weight of book. All right, so since this equation has only one unknown in it, namely this term, we should solve for the force of the bicep. And then this one right here, we should rearrange to solve for the force of the elbow. So force in the elbow is force of bicep minus the weight of the arm minus the weight of the book. Now note, the weight of the arm is given by the mass of the arm times the gravitational acceleration. Mass of the arm was given up here as 2.5 kilograms. So this is 2.5 kilograms times 9.8 meters per second squared. So the weight of the arm is going to be 24.5 newtons. And similarly for the book, the weight of the book is the mass of the book times the gravitational acceleration. So that's 4.0 kilograms times 9.8 meters per second squared. And so this weight of the book is going to be 39.6 newtons. And if we were keeping track of significant figures, this is actually 25. This is actually 40 newtons because there's only two significant figures for each. All right, so let's go ahead now and solve. So force of the force of the bicep is going to be radius 2 over radius 1 times the weight of the arm plus radius 3 over radius 1 times the weight of the book. So that means that we have 4 centimeters was radius 1, 16 is radius 2, 38 is radius 3. So we would basically be able to eliminate the centimeters part of that and just take a strict ratio. This is basically 16 over 4.0 times 24.5 newtons plus 38 over 4.0 times 39.6 newtons. And so the bicep in this case is applying a total force of 470 newtons. All right, so then we can go back and find how much the elbow is, or the triceps are applying. And so that would be 470 newtons minus the 24.5 newtons minus another 39.6 newtons. And so the force applied by the elbow is going to be 406 newtons. So we've got both forces. The other part was how do these forces compare with the actual weight of the object being held? Well, 470 is almost 10 times more. In fact, it's more than 10 times more than 39.6. And this is also about 10 times what this one is. So you need about 10 times as much force here as what you're lifting here. Suppose the arm were to get longer. What would happen? Well, basically, you'd end up needing even more force here and here. With one exception. If the whole arm gets longer together, then that can also mean that this radius part here is getting proportionally longer. And if that's the case, then actually everything should stay the same. If everything is getting linearly longer together, if you double this one, and this one, then the bicep force remains the same, and the elbow force, therefore, also remains the same. If you quadruple all of them together, bicep force remains the same, elbow force remains the same. Of course, the guy would then have freaking huge arms, but nevertheless, there's no change in the amount of force applied based on how wide this arm gets. With that said, this joint may not necessarily remain proportional to the length of the arm and to the length all the way out to the hand. In that case, you'd see a difference in the bicep and therefore in the tricep muscles. Our next example is here to illustrate why we shouldn't lift with our backs. Why is it that you're supposed to lift with your legs and not with your back? So what's going on in this figure is we can basically treat this back system or this guy as acting like a lever in a sense. And the relevant thing to draw here is we have our pivot point, which is this red dot. And basically the back muscles are applying some force along his spine. And that is this F back, which is the thing that we're actually needing to solve for. And this distance is given as 8 centimeters. So this actually is perpendicular. That's one of our distances. Now the other end is that there is a distance of 50 centimeters from that same pivot point to the center of gravity for the box. So this would be weight of box, WBOX. And then similarly, his actual spine is kind of doing a number like this, and his actual center of mass for his upper body is right here, and this distance right here, this perpendicular distance, would be 35 centimeters. Okay, so those are the relevant distances, and this is the basic diagram that we need. Basically, we're going to use sum of torques is equal to 0. And what that implies is we have a clockwise, we have a clockwise, and this right here is actually a counterclockwise. So we would basically say force of back times the pivot distance, whatever you want to call this distance. We'll call it RB for back, minus the weight of the upper body, W upper body, times the perpendicular distance, R perpendicular upper body, which is this distance, minus the weight of the box times the R perpendicular for the box. So this is equal to 0. Therefore, the force exerted by the back must be this weight of the upper body times the radius for upper body over radius to back, plus the weight of the box times the radius for the box over the radius for the back. And so that is going to be given by mass times the gravitational acceleration times each of these radii in turn. So the weight of the upper body is given by the 60 kilograms times 9.8 meters per second squared times the radius, which was 35 centimeters, divided by 8 centimeters. And then the other term is given by the mass of the box, which is 25 kilograms times the free fall acceleration times the distance, which is 50 centimeters, divided by 8 centimeters. So the force that the back is going to need to exert in this case is about 4,100 newtons. So that's quite a bit of force just to lift up a 25 kilogram or 250 Newton-ish box. And notice if we were to change this diagram just a little bit, in other words, if he were to stand a little more erect upon lifting, then his center of gravity might be more like this in comparison. The force that the back muscles are exerting is same perpendicular distance from the pivot point, and the distance out to the box would be also somewhat lessened, and therefore he would have to exert a lot less force from his back muscles in order to lift the box, and hence he'd have a lot less risk of damaging his back in doing this. The other question in here is, what is the magnitude and direction of the force exerted by the vertebrae at the pivot point? So that's this little guy here. There's basically, in other words, a force going up along here in order to stabilize the entire system. And this force cannot be perpendicular to the back muscle because it needs to both balance out this and these other two forces. To solve for the force of the vertebrae, both magnitude and direction, what we do is we use the other condition for equilibrium, which was Newton's first law. And so that's basically that the sum of forces must be zero. I've gone ahead and drawn a free body diagram here, which shows the basic direction of all four forces. And you can see that there's going to be x and y components. So here's FVy, here's FVx, and then for the box, here's FBy and FBx. And basically we can write that the force in the x direction for vertebrae minus the force of the box in the y direction should be zero. And similarly, that would be the force in the x direction here. Box x is equal to zero. And similarly for the y directions, FVy minus FBy minus weight of box minus weight from the upper back must be zero. So what we do is we need to basically solve for the x and y terms of this and then use Pythagorean theorem to get the total vertebrae force and use the tangent of theta is Vy over Fvx. So in other words, the total force of the vertebrae should be the square root of the x component squared plus the y component squared of the vertebrae. And similarly, the tangent of that theta, that angle theta, which gives us the direction, should be the y component over the x component. So to do this, basically Fvx is equal to Fbx, which should be equal to Fb times, if you look at this triangle, the cosine of 25 degrees. So given that Fb is 4100, what this basically means is that the x component is going to be given by about 3,715. So we'll just call that 3,720 newtons. The y component, FVy, is going to be given by the sine. So I'm going to go ahead and solve for FBY here because we need to plug that into this equation up here. FBY is FB times the sine of 25 degrees, which means that this y component of B is going to be given by 4,100 times the sine of 25, which is going to give us approximately 1,733. So we'll call this 1,730 newtons. All right, well, we've solved right here for the BX part. For the FVY part, we're basically therefore going to have 1,730 newtons plus 245 newtons plus 588 newtons. And that's just using this and this and this. So that means that the total in the y direction for the vertebrae is going to be about 2,565 newtons. So roughly 2,500, and actually if we round off, 2,570 newtons. So then using these two equations, that implies that the total force should be 4,519 newtons. And for the angle, we take the inverse tangent of the y component divided by the x component. And so what we end up getting is about 35 degrees, 34.6 degrees. So this basically means that the vertebrae is giving us a total force of about 4,500 newtons in the 35-degree direction. So that is, once again, quite a bit of force, given that we are only trying to lift up a 245 Newton box. Last but not least, I want to look at some example with a firefighter climbing a ladder that's leaning against a house. So we'll take the ladder to have some mass, and then some given length. We'll give the firefighters some mass, and we'll give a coefficient of friction of 0.35 between the ladder and the ground, with no friction between the wall and the ladder. And so the question is, what is the range of angles that we can balance this ladder against the wall without the firefighter being on the ladder? And then what are the range of angles that the firefighter can make it to the top of the ladder without the ladder slipping? All right, in order to solve this problem, it may be helpful to begin by drawing a couple of diagrams. One is just a simple diagram of the ladder, which is maybe like this, and I'm going to draw in the forces and the angles. Here's angle theta. This is the angle that we're solving for. We'll call this angle phi, which is 90 minus theta. The forces that act are going to be the normal force between the ladder and the wall, the force of gravity, which acts at the center of mass for the ladder, the normal force between the ground and the ladder, and then also a force of friction between the ground and the ladder. And this force of friction, we should recall, must be less than or equal to the normal force between ladder and ground times the coefficient of friction. All right, so those are the forces and where they are acting. That we're going to want for when we do torques, if we do torques, and we will. The other thing we can draw is a simple free body diagram which organizes the forces for doing Newton's law. So there's the upward force provided by the ground, force normal for ground. There is a downward force, which is the weight of the ladder. There is a force from friction. There is a force from the wall acting upon the ladder. So that would be this guy. So Newton's law basically is showing us sum of forces equals 0. Basically says that the normal force between the wall and the ladder is equal to the force from friction and the ground, and then the force between the ground and the ladder, the normal force from the ground to the ladder, should be equal to the weight of the ladder. So that is basically like this, mu F in G. All right. This looks like two equations and two unknowns. And in fact, there is some coupling between these two equations. However, none of these equations really have the angle theta in them anywhere. So what we need to do at this point is go ahead and use the torques equation to try and figure out what the angle is. Another way of looking at it is that there's coupling thanks to the fact that I brought in the mu times the force between the ground and the ladder, but there's no angle involved anywhere. The original two equations would be these two sets of equations. And if you looked at just these two sets of equations, there's no coupling between equations. There's two terms in this one, and there's two different terms in this one. So now let's go ahead and do the torques side of the equilibrium. So we got to look and see which direction does everything make this ladder want to spin, or in other words, in which direction does each torque act. I'm going to choose this to be my axis of rotation, and I am going to choose to call the length of the ladder L. So L represents the total length of the ladder. Basically, these two are acting at the axis of rotation, therefore they produce no torque on this ladder at this axis of rotation. So now we need to use the other two and see which direction their torques act in. So this angle right here, by the way, is also going to be theta. This angle right here is also going to be equal to phi. And what we see is that this torque right here tends to make the ladder spin in a counterclockwise direction. This one tends to make it want to spin in the clockwise direction. So our sum of torques equation basically is going to give us that the length times the normal force between ladder and wall times the sine of the angle between them minus the length over 2 times the weight times the sine of the angle in between those is equal to 0. So this basically, we can eliminate the L's from this, and basically you end up with the normal force between wall and ladder times the sine of theta is equal to half of the ladder's weight times the sine of phi. Now, phi is 90 minus theta. So phi is 90 degrees minus theta. Again, we see this geometrically because this is a right triangle. Here's phi, here's theta. What this implies is that the sine of phi is the same thing as the cosine of theta. So this right here gives us 1/2 times the weight times the cosine of theta. All right, so at this point, we now can start combining some equations here. This one right here, the normal force between ladder and wall, was less than or equal to mu times the normal force between ground and ladder. And ground and ladder was equal to mg. So substituting this and this in for this normal force between wall and ladder, what we end up with is that Fg times mu times the sine of theta is equal to 1/2 of Fg times the cosine of theta. And so this is not actually a true equality though, because this guy right here is greater than or equal to this. So we need a greater than or equal to sign over here to make that work out. And if we divide both sides by cosine of theta and we divide both sides by Fg mu, what we end up with is that tangent of theta must be less than or equal to 1/2 mu. The Fg's basically cancel. So what this basically means is that we've now solved for the range. The range is between 0 on the low end and then 1/2 times mu times this tangent on the high end. So if you put in the value for mu, which was given up here, mu is 0.35, this basically becomes 1/0.7. And so the tangent of that gives us 55 degrees. So this is the range of angles for which this ladder should be able to remain upright against this wall. Suppose we now have the condition that a fireman needs to be able to climb the ladder. What's going to change? Well, basically this is what our new diagram would look like, showing forces acting on the system. We add in one additional force for the firefighter, and our free body diagram now looks like this. There is still the normal force between ladder and the ground, still has the frictional force between ladder and ground needing to balance out the normal force between the ladder and the wall. This time, however, there are now two downward forces. One is the weight of the ladder, the other is the weight of the fireman. So basically what this ends up doing is modifying each of our equations just slightly. For example, Newton's first law basically now gives us the following conditions. First of all, the normal force between ground and ladder is going to be equal to the weight of the ladder plus the weight of the fireman. The friction force actually is still going to be equal to the normal force between wall and ladder. So that one's not changed. So far the main change is by adding this term here. Now if we include torques into the mix, we're going to take this to again be position 0. So this equation now basically says that the torque that is from the normal force on the wall, which is like this, times the sine of theta, minus the torque from the ladder's weight, which is basically L/2 times weight of ladder times the sine of phi. And now we have to include the fireman's torque, which actually also is clockwise, so it's basically another minus L/1, since it's at the full length away from the axis of rotation, times the weight of the firefighter times the sine of this angle phi. And all of that should be equal to 0. So if we cancel our like terms out, get rid of some L's, and again recall that sine of phi is the same thing as cosine of theta. So we're going to divide everything by cosine of theta, and what we end up with is that normal and wall times the tangent of theta should be equal to the 1/2 of the weight of the ladder plus the full weight of the firefighter. All right, so that's a slight modification. Now we go back over here and recall that this right here is also equal to the force of friction, which has to be less than or equal to the coefficient of friction times the normal force with the ground, which in turn is the coefficient of friction times now the weight of the ladder plus the weight of the firefighter. So that's our other modification. So we're going to want to divide this term from both sides, and what we end up with is that the tangent of theta needs to be less than or equal to, that would be this substitution, 1/2 of the weight of the ladder plus the weight of the firefighter divided by mu, the coefficient of friction, times just simply the weight of the ladder plus the weight of the firefighter. Notice that there's a factor of 1/2 multiplying just this term here. That's not down here, so we can't be canceling numerator and denominator. Basically, the numerator is now going to be 1/2 times 14.0 kilograms times 9.80 meters per second squared plus 90 kilograms for the firefighter, also times 9.8 meters per second squared. So our numerator is going to be given by 950.6 newtons, and the denominator is going to be given by mu is 0.35, and that's going to be times 14 kilograms by 9.8 meters per second squared plus 90 kilograms times the same. And so all of this right here is going to give us 356.72 newtons. So basically, we're going to end up with 0 is less than or equal to theta, which is less than or equal to the inverse tangent of this divided by this. So basically, that is going to be the inverse tangent of 2.66. So if you take the inverse tangent of that, you get 69.4 degrees. So theta needs to be between 0 and 69.4 degrees in order for this firefighter to be able to climb up to the top of the ladder, which may be contrasted with the result we got previously with no firefighter. 0 to 55 degrees would be okay for the ladder to stay stationary. All right, so at this point we've solved through a few different examples using the concepts of static equilibrium. Basically, sum of forces is 0, sum of torques is equal to 0. Hopefully you got a lot out of this particular video, and I hope you at least found it to be helpful. And thanks for watching.